So I want to talk about 12 speedy tricks for answering NP-complete problems. Perhaps you know what NP is. If not, I want to give you a short introduction. NP is, first of all, a class of problems. Problems with a yes-no answer. So we give the computer a problem, and the computer should find out whether the answer is yes or no. Those NP-complete problems occur naturally in many areas, in logistics, in optimization, in scheduling, whether it's processor jobs, worker shifts, anything else, in hardware and driver verification. So if you're using a recent Windows operating system, then probably some of the hardware drivers have been checked by some tool where deep down there is an NP-complete problem. So what makes a problem NP-complete? The first thing is, well, it's on a list of NP-complete problems, because there are nowadays lists with hundreds of these problems, and one of the most cited books in theoretical computer science is basically a list of several hundred NP-complete problems. Okay, so to give you an intuition, the intuitive explanation of what NP-complete problem means is that if we have a solution, it's very easy to verify that the solution is correct. But finding the solution, on the other hand, is very hard. So further properties which are very interesting is that all NP-complete problems are translatable into each other, which with relatively inexpensive computational time required to do so. So if we have an algorithm for one NP-complete problem, then we can use this algorithm to solve all NP-complete problems. So some of the most prominent ones, maybe you have seen traveling salesman, the graph colorability problem, the knapsack problem. If you don't know these, maybe you know Tetris, which is also NP-complete if your gaming area is large enough, or even Minesweeper, which is also NP-complete if your gaming area is large enough. Here, for example, you can see some simulation in Minesweeper of an AND gate. So there is a mine at the end of here, and there are some mines. Yeah?
How is the solution of the traveling salesman easily verifiable?
Sorry?
Like, how do you verify the solution of the traveling salesman? Like, you have to check all the alternatives and find out whether you're actually on the shortest path, don't you?
It depends how you formulate the problem. If you formulate it as a decision problem, so having a yes-no answer, the question is, can I with these weights have a path? And then it's very easy to verify. Of course, for the optimization problem, you need linear time. Or you need to check that it is not possible in less steps. So then you have also a verification of the... So you first see, is my salesman is traveling in, let's say, 15 steps around. You check this is correct. And then you check if there is no answer for 14 steps. Okay. One of the first NP-complete or problems discovered to be NP-complete, the most prominent one, and the one I think which has been worked on the most, is the satisfiability checking, or SAT problem. I would like to go here into detail. So propositional satisfiability checking. We have basically two ingredients. The first one is we have Boolean variables. So A, B, whatever you like to name your variable. And this variable can have two values. It can be either true or false. And the second ingredient then are clauses, where you have statements which say, well, a variable or some other variable or some other variable or a possibly negated variable, one of these should be true. So the first clause here in this line says A or B or C is true. there is another representation of the same clause, so I prefer this one because I'm having a logic background, so this is just the same expression with logical symbols. If you prefer C or Java, then this would be the same expression. It's just a Boolean expression where you have Boolean variables and possibly negated ones, and you connect them with an OR. So a clause then is satisfied whenever the expression evaluates to true. This means that at least one positive variable is assigned the value true or 1, and or a negated variable is assigned the value 0. So quick example, if we have the assignment A is true and B is false, then the first clause is satisfied because here A is true, and the second clause is also satisfied because here we have not B. B is false, the negation of B is true, so therefore something, something, or something true evaluates to true. Now the set problem is given a set of clauses, find a truth assignment for my variables such that all of the clauses evaluate to true. That's it. And an instance of that is then, well, a concrete set of variables and clauses. So now I said NP-complete problems are easy to verify but hard to find. What does this hard to find mean? Well, it means that if we want to have a correct algorithm which is giving us the right answer every time, then this algorithm has an exponential time requirement in the worst case, which means that exponential time, suppose we have an algorithm and for 3 variables to say whether the set of clauses with these 3 variables is so if there is satisfiable, so if there exists an assignment and we need 1 second, then it means that if we have 13 variables, we need more than 1,000 seconds. If we have 35 variables, then we need more than 4 billion seconds, which is more than a century of time, which we clearly don't have. So this is, I mean, hard to solve. So the question is, of course, can we do better? And the answer to that question is unknown, because this is actually the famous P versus NP problem. So NP is the class of problems which are hard to solve. P is the class of problems which are easy to solve. And we don't know if there exists an faster algorithm, an algorithm which is correct, but requires less than this exponential time. And if you know the answer, you can call yourself a millionaire, because this is one of the Millennium Prize problems. And the Clays Institute of Mathematics said that they will pay you $1 million if you get a proof published showing that whether those 2 classes are the same or they are not the same. But at the moment, we don't know. If you look on the practical side, however, so there are set solvers, so solvers which can answer the set problem for us, where we give just a set of clauses, and then they will, after some time, they will tell us, well, yes, I found a satisfying assignment, and here it is, or no, there exists none. And today, those solvers are able to solve instances with up to 500,000 variables in less than 10 minutes. So this means we have a search space of 2 to the power of 500,000 possible assignments to check. This is huge. For reference, the size of our observable universe contains about 2 to the power of 280 atoms. So we really have to search much, much more than our universe contains atoms. And apparently, these SAT solvers today are able to do this. So how is this possible? Well, the answer is the exponential searches for the worst case. And in practice, there exist many tricks such that we don't encounter this worst case, or tricks which make the worst case go away, where we previously thought, hey, this is really a worst case, but well, if we are clever, then it turns out it's easy to solve. And well, these tricks for shortcuts. This is what I will present to you, some 12 of the, I think, very important ones. But first, let's look a bit into this, why do we have this exponential time requirement? So where does this exponential blow-up come from? If we have two clauses which contain the variables a and b, so we have two variables, so for the variable a it can be true or it can be false, and for the variable b it can be true or false, and in both cases whether a is true or false. So this is for two variables. If we now add another clause which contains a c, then of course we get for c, for each of the previous cases, we now get the possibility that c is true or false. So we have a binary tree, and a binary tree has exponentially many leaves with respect to its height. So this is where this exponentiality comes from. We can then verify an answer. For example, here, if you set a to true, b to true, and c to true, how do we verify this? Well, we simply walk over all the clauses and check if they are satisfied. So for example, the first clause, a or not b, a is true, so therefore the clause is satisfied. Second clause, not a or b, b is true, so therefore the second clause here is satisfied. Third clause, not a or c, c is true, so therefore the third clause also is satisfied. So this is easy to check that this is a satisfying assignment. But well, to find an answer, we now, because we don't know if there is a one, or as in this case, this assignment here evaluates to 0. So it's not satisfying those clauses. Why? C is 0, so the third clause here, not a or b. A is true, so not a is false, or c is false, so this is false or false, so this means the clause is not satisfied. So therefore here we have a 0. It's not a satisfying assignment. And we can check this for all the others, but we don't know where the ones are. This is basically the problem. So now for the tricks. The first one. In case of doubt, well, just do the right thing. So yeah, that's easy. We have this tree with the binary decisions, and we have some zeros and there are some ones. So all we have to do is, well, take the right path to get to the ones directly straight ahead. And this approach is called heuristics. So we try to come up with some small algorithm which is guiding us through this binary tree here and telling us leading us directly to the ones. So one example for such an heuristic is this D-list heuristics, which at every step in the tree looks at all the clauses which are not yet satisfied, and then it just counts how often occurs something positively or negatively, and then it tries to pick an assignment such that the most clauses are satisfied. For example, if I go down here and I have these two clauses not satisfied, then I can count for the not B occurs twice, and not C or C, this only occurs each assignment once. So not B is one assignment making more clauses satisfied, so I pick not B. So I assign to B the value false. Yeah, this is what I just explained. Okay. Second trick, heuristics are really nice, but they can be a waste of time because the guess may be wrong. The heuristics may lead us into the wrong direction, taking the wrong branch. Also, the heuristics usually help us only in finding the yes answer. So if we are given a set of clauses and this set of clauses is unsatisfiable, meaning there are all zeros at the bottom, how can the heuristics tell us? It is just leading us to one of the cases, but to be sure that there is no answer, we have to check all of them. So in the worst case, the heuristics is just a waste of time, because in this well, in these cases, it does not tell us, but it consumes time to compute. So the conclusion then is that, well, checking more assignments is better than guessing one good assignment, which then also means that we really prefer speedy heuristics, even if they give us worse results. So a heuristics which leads us more often into the wrong direction, but consumes only very little time, is in the end better than a heuristics which consumes more time, but is leading us better to the satisfying assignments. Well, even better than doing all those guesses is don't guess at all. Try to know. So here we have a case. We again have some clauses. We pick the assignment that A is true. So this clause here is already satisfied. And if we look at those two clauses now, we can see that, okay, A is true, so not A is false. And now there is only one variable, a negated one here and a positive one there, in the clause remaining. So for this clause to be true, it must be the case that C or not C evaluates to true. So this means that C must have the value false. So in this case here, because this A can no longer contribute to making the clause satisfied, we now know there is only one variable remaining, which has no value yet. So this means we know which value to pick, because otherwise it would be wrong. So we now directly know, okay, C must have the value false and B must have the value true, without guessing. So yeah, and this condition here that the variable has everything unsatisfied except one remaining variable, this is called unit. So the clause is then called unit because there's only one possible variable left to make it satisfied. And the technique is called unit propagation, and this is one of the most important techniques in the set solving because it solves us a lot of guessing. We directly know what to assign to a variable. But this only works if there's one variable remaining in the clause. If there are multiple ones which have no value yet, then we have to guess. Okay. Well, while doing this propagation, it turned out that it costs a lot of time. Set solvers a few years ago, you took about 90% of their time for just doing this unit propagation. It was very costly to do. So one of the further enhancements is to be lazy. Because if you're lazy and you work the same time, you get more things done. You're more efficient. So the next step was to use lazy data structures to find out which clauses are unit. Because for example, if we have A is true, then we get C is 0 and B is 1. So for this assignment, C is 0 and B is 1, and also for the one here for A, we have to go through all the clauses and delete them from the clause so that we realize later on, this clause has now become unit. So for the C, we have to check all the remaining clauses where there is a C, and we have to delete it from the clause or somehow mark it that it does no longer contribute. So this results in many checks, many clauses to be processed every time for every assignment. And we can actually be more lazy by not checking every clause where the variable occurs, but only for each clause having 2 pointers. So we don't store anymore, hey, we have a clause, there is a not A, a D, a E, a C, and a F, but we only store, hey, we have a clause, and on the left-hand side, the leftmost variable is a not A, and the rightmost variable is an F. Because now if we assign to A the value true, what we just do is we look at all the pointers. If there is a clause where the variable A occurs at the leftmost or rightmost position, and then we mark this as deleted and we move the pointer. So for each clause we only have 2 orders to check. And for the assignment that C is 0, in this case here we don't have to do anything. So we don't have to process any clause because there is no border is C is none of the border variables. And of course then, so what we then do is by making more assignments, we are pushing the border variables together until finally there is only one variable remaining, and then the clauses unit. So, so for example, if we assign to F the value false, then we will move the border variable, then we will point to C, and then we will have, okay, C is also false, so we then move the border variable 1 next. So this postponed a little bit of the processing, but in the end it really helps. Because if we do wrong assignments, then we save a lot of time if we do backtracking later on. Okay, so being lazy. And this is also a very important trick. Learn the structure of your problem. Because if you get an instance of a set problem, then it is often encoding something in the real world. And things in the real world are connected to each other. Or one thing is influencing something else. So for example, here we have the clauses A or B and not B or C. So A and C do not occur in a clause together, so they seemingly are not related to each other. But there is a structural dependency between those two. Why? Well, via this B. In fact, it must be the case that A or C must be true. Why? Assume that A is false and C is false. Then A is false, this means that B must be true. C is also false, this means that not B must be true. So B must be true and false at the same time, which is not possible. So therefore, A or C must be true. One of those two must be true, otherwise we don't find a value for the B. Otherwise, every value for the B will be a wrong one. So we can directly learn a new clause, which is A or C. And this clause now connects two things which previously have not been connected. So this shows some structure. This procedure here is actually called resolution. It has one problem. There are exponentially many possible resolutions. So if you start with your set problem and your clauses, and you want to, and you directly start resolving things, then you get exponentially many resolvents. You get exponentially many new clauses, and in the end, you have just run out of memory, and it didn't help you anything. But next trick is, where this is beautifully working, learn from your mistakes. So if we have an assignment that violates some clause, then we can use resolution, starting from this violated clause, going backwards, and uncover things which are important, which we did ignore because we run in a mistake. And this, for this, we need some additional data structures, which I don't have the time to explain now. This is called an implication graph. Here we record those propagation steps we did before, where we realize, now some variable must have a certain value. This is recorded here. And then we can use this graph to going backwards, resolving, learning a new clause. And the important thing is that this learned clause now helps us to avoid similar mistakes in the future. So this learned clause is now cutting off parts of our search space. Previously, we would have thought, okay, so we are now at some position, and over there in our tree, there might be some satisfying assignment. But now we've run into a mistake. We have learned some clause, and through this new clause, we will never go there because we know all the time, okay, there is no solution at all. So this is really cutting off large portions of our search space, and this gives some exponential speed up. So this is a very important technique. Now then, of course, there's the question, okay, what do I really learn now? Which clause should I learn, and how do I use this data? It turned out that some learning schema, which is called the first UIP, is the best in practice. First UIP is like the graph dominator closest to the violated clause. This is this node here in this specific graph. But let's go to the next trick. Sometimes we make a bad decision. We make a bad assignment, but we don't realize this yet. And then we continue on and we continue on. For example, here we made a bad assignment for A. We picked A is true, and we have these clauses over here. So everywhere we remove the A, so then we have X and Y remaining. But you may see there are all possible combinations of X and Y. So for every combination of X and Y that we will later on find, there is one clause which is violated. So if we go back a step, then we actually see, okay, the assignment for B, the assignment for C doesn't matter. It is the assignment for A which is the wrong one and which makes us fail. But if we now do the traditional backtracking, so we are down here in the tree, for X is 0, it failed, so we try for X is 1, it will also fail. Then we go back to C is 1, we will remove this assignment, make the other one C is false, and then we try for X again, and then it will fail again, and then we go back until B. So what we would much more likely do is directly go up here to the A. Because this backtracking must try all combinations, also for the unrelated ones, because we don't know that these are the unrelated one and the bad guess is actually over there, the A. But the trick here is to directly jump back. So do a back jumping, recognize that the bad guess is happening here, and directly backtrack to this. How do we recognize this bad guy over there? Well, the learned clause can tell us this, if we do this correctly. So we need some side constraints to do this, but this works with the first UIP scheme I told you previously. So then we can jump directly back here. Okay, so remember the heuristics that guide our search. It turned out that heuristics are most effective if they are not static, but if they dynamically focus on problematic variables. So a problematic variable is one which occurred recently in a newly learned clause, because it has something to do with some mistake that we made. So one of those heuristics is called the visits heuristic, and I'd like to show you how this works. It has a counter for each possible assignment. So if we learn the clause A or not B, then we increase the counter for A being true, and we also increase the counter for B being false, because they would both satisfy this clause. And then after some time, we decrease all the counter values. So this is like some time decay, which means that we will most likely pick, so then we pick a variable with the highest counter number, and this will be a variable which occurred most recently in one of the learned clauses or in multiple of the learned clauses, so that we really focus on problematic variable assignments and try these variable assignments first. So we don't try the unrelated, the easy ones, we try the hard ones first, which make the problems. Okay, next trick. Think before you even start. The idea is to analyze my input data, analyze my clauses, and remove some of them. And for example, one of the things we can do is for removing variables, if we have two clauses, A or not B, and another clause not A or B. Then if A is false, then B must be false. And if A is true, then B must be true, and vice versa. So what these two clauses are telling is that, well, actually, the value of A must be the same as the value of B in any case, because otherwise one of those two clauses will be violated. So what we can do here is we simply remove the B and replace the B by A in all the remaining clauses. So we got rid of one variable, which means half of our search space is already done. There are multiple possible optimizations, so check for unit clauses first. And so if we have a unit clause, then this means, okay, D must always have the value true. So directly pick this. There are many more. Removal of pure literals, look-ahead probing. All of those pre-processing steps is they shrink our search space, which is very good. But, well, sometimes we are just stuck in a bad region and nothing helps. The learning doesn't help us, the back-jumping doesn't help us, pre-processing also was of no help. So we can't do anything. We are encountering one wrong assignment after another, and we really see no way out. But luckily, in IT, we have a standard procedure for that. Have you tried turning it off and on again? And surprisingly, for SAT solving, this also helps. So what we do is we simply drop all the assignments and start completely new. But what we keep is, first we keep the learned clauses. So all the mistakes we did in the last time, we will not do again. And also, if we have our heuristics a little bit randomized, then this means we will go to another part of our search space. So this then means that we are, well, approaching from a different angle or from a different perspective the same problem and maybe see a solution then. Of course, with those restarts, you have to be careful to not turn your solver into something incomplete. So for the completeness, you iteratively have to search longer and longer until you restart again. Because it might be the case that, well, if I restart after 10 failures, but after 11 failures, I would have seen that, okay, there is some solution or then I have to do those 11 failures. I cannot always just stop at 10. But this is also possible. Okay, so trick number 11, adapt to the world. If we look around us, then we have in every computer, we have a memory hierarchy. We have the CPU registers, we have level 1 cache, level 2 cache, some maybe 3 and 4, and then the RAM. And they are all increasingly larger, but increasingly slower. So the CPU registers are really the fastest memory in a PC. Then comes level 1 cache, and then after this comes level 2 cache. So what we would like to do is stay closest to the registers or stay closest in the cache. And we can do something here, because if we think about the case that, well, we have assigned the value true to A, and now we have to update all the clauses which contain A for this unit check. So even if we have this lazy data structure where we only have the pointers, we still have to process all the pointers. So we will have in memory some list or a vector for all the locations where A is occurring. So list of pointers. And this vector now usually has a head and data. The head means there is stored the size, the capacity, and a pointer to the actual data. And the actual data, this is something we have malloc previously, where then the pointers are stored. And this means if we want to read in the data, we have 2 cache lines that we have to read. So the first cache line is where the information from the head is stored, and then the second for the data, for the actual data. But the observation is that, hey, the head is much smaller than 1 cache line for most CPUs. So what we can do here is we put some data into the head. So in the head, instead of just storing size, capacity, and a pointer to the data, we store size and capacity, and then as many data as there fits into the 1 cache line, and a pointer to further data. This means that if A is only occurring in 12 clauses, then we only need 1 read for the head of this vector and not a second one for the data, because some of the data is already in our level 1 cache. So this helps to avoid many cache misses. So this is called cache-conscious data structures, and it's really the case that modern SAT solvers, if you start them, they first query your CPU, what type of CPU do you have, how long are the caches, and then they adapt their internal data structures to optimally fit in there. This makes some additional gain of 20 to 80%. Okay, and then this last trick. Every one of you probably has a computer with more than 1 core, because nowadays we have all those multi-core machines. So the question is, how do we use this parallelism optimally? The naive way is divide and conquer. I pick a variable, and then I say, okay, the CPU 1 works on every assignment where on V is true and everything there, and the CPU 2 works on the other one where V is false. So we split our search tree, 1 CPU working on the one, the other CPU on the other one. This means that for each of the CPUs we have the search space halved, which is very nice, but we can do better. Because there is something which is called a search strategy. This is a selection of heuristics for pre-processing, variable selection, restarting, etc. I've shown you a few heuristics right now, but if you read the manual of one of the SAT solvers, then you will see that you have a plethora of 200, 300 heuristics where you can select which one you want for which task, which is, you don't know which one you should pick. This is the problem. So if you pick a good search strategy, then many problems are solvable. If you pick a bad search strategy, so if you pick the wrong heuristics to use, then you will not find an answer. So since it is hard to know a good strategy, we apply the parallelism not on the problem itself, but on the search strategies. So what this means is that CPU 1 works on the whole problem, but it uses one strategy, and the second CPU works also on the whole problem, but it uses a completely different search strategy. And we share learned clauses. So the structures that both of them uncover, they are shared, so they are profiting from this. This means that we are actually approaching the problem from multiple directions in parallel. And this has much more impact than using just this divide and conquer. Okay, so to give you a summary for fast SAT solving, first trick, in case of doubt, do the right thing. Second, well, do it, but don't invest too much time in this heuristic stuff. Even better than guessing is knowing, which is trick 3. But then also be lazy, because this means being more efficient. Learn the structure of your problem. Learn from your mistakes. This helps the most. Try to get out of bad situations, but also focus on the bad guys. And before you start, think a little bit. You can make your problem much easier. If nothing helps, do what you always do, just restart and adapt to the world and use parallelism correctly. Okay, so for the last parts I have shown you what you can do with, or how you can solve set and NP-complete problems, because every NP-complete problem is translatable into set. So if you are really working with them, this clauses is rather inconvenient. What I am doing is I'm working with a more convenient language, which is called answer set programming, where I have everything written down in some if-then rules. So here I have written a rule which says if I have some x and this x is a bird and it is not a penguin, then this x can fly. So this is, if this is true, then this also should be true. There are some tools for working with this languages called CLASP or DLV. In the background, we all the time have those set solving techniques, sometimes a little bit enhanced. If you want to go beyond NP, so if you want, for example, outside information or richer theories for set, then you can use what is called SMT, set modulo theories. Microsoft has a very prominent tool there, which is set3, which is also used to verify your drivers in your operating system. And for answer set programming, there is a tool which is called DLV Hex. This is where I am working at. And to show you the power of this, I would like to show you how you do Sudoku. So you know Sudoku, you have those tables where you, in each position, you have to put some number between 1 and 9, and you have some conditions like in every column there is each number exactly once, in every row there is each number exactly once, and in every of those 3 times 3 subtables each number occurs exactly once. So if you want to find all the possible answers to this Sudoku, then with answer set programming what you have to do is, well, you have here one rule, you have here 2 rules. So this one says if I have some value x and y, which are between 0 and 8, so somewhere in my whole table, then I have either a 1, a 2, a 3, 4, or a 9 at this position. Here this line says if I have some row and I have 2 columns and the columns are different and the number is the same, this means I have twice the same number in one row, then this must not be the case. And this is for the columns and this is for the subtables. And this here is my encoding for the actual input. So this is actually the whole program to solve Sudoku in 3, 4, 5, 6, 7, 8, 9, 10 lines actually. Yeah, thank you. Okay, so you get an answer, and this is the end of my talk. Thank you. Questions? Yes?
How fast is the Sudoku solver compared to other approaches like
It depends if you have a Sudoku where you only have one possible solution. So this one here will find all the possible solutions if there are multiple. To be honest, I did not compare it with other Sudoku solvers, but we are speaking about 0.1 millisecond. So this is basically the range for Sudoku, because Sudoku is quite easy. Yeah. Yes?
Just kind of, because you say that is the whole code which is behind the Sudoku solver, but the real code is your SAT method, right?
Yes, 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 yes,
much
yeah.
richer.
Yeah, yeah, yeah.
But
so, yeah, this is the code for the answer set program, but this is the thing I'm actually writing down. The Others, the set solving and those tools, they already have been developed. So I'm just using a tool. Just starting a solver with this input. That's it.
Are there other examples of problems that you have already solved like this, or that would be interesting to be attacked from this point of view?
You can encode free colorability, I think, with 2 rules, 2 lines of code. So they are really good at solving NP-complete problems. They are not good at solving problems where you think are easy from a programmer's perspective. So it's hard to play Tetris with this programming language. We're working on that, but yeah.
Are there kind of additional assumptions in your solver, like that the number of clauses is small than x of the number of variables? So in principle, you could have 2 to the number of variables clauses, or that your clauses are short, that they contain few of the variables only. Because some of your reductions kind of seem to be geared towards small clauses.
Yes, yes. Small clauses is what the set solver really wants to have. So the goal always is to get small clauses. The reason I have only small clauses here is because otherwise the examples become just too big. The set solvers, the benchmark instances with those 500 or 300,000 variables, they have, I think, 1 million up to 10 million clauses, but not more. So it's roughly
to the number of possible clauses.
Yes, this is. But if you have, so if you're speaking about the relationship between number of variables and number of clauses, if you have, for example, many clauses with respect to your variables, then there might be other approaches which are faster. Or, well, the solving also probably turns very easy then. Because if you have many clauses, it is easy to see that you don't find an answer, or where all the bad answers are. If you have only a few clauses, it is very easy to find answers. There is some kind of, if you generate randomized instances and then you put them on a line with the number of clauses or number of variables divided by the number of clauses, and then you see some kind of phase transition. So it's very easy for the yes instances. Then there is some point where it goes up, and so almost everything is a yes instance, and then almost everything is a no instance. And only at this vertical point, so to say, these are the hard instances for the solvers. If you have randomized
probably not much
things.
better than try.
Yes, in the worst case, and then this is still true for the set solvers. So they are a complete and a sound procedure to find out whether a set of clauses is satisfiable or not. And this means there must be some examples where the solver really has problems and needs exponential time. Otherwise, if there don't exist any, then I've just solved the P versus NP problem. Yeah. Yes?
So how well does this set solver perform when you give it a problem, a transform problem from another NP hard problem? So you can transfer NP complete problems to this hard problem, but does this heuristics transfer as well?
It works relatively well.
Okay.
But it might be the case that your transformation is not very good. So by meaning there is a translation, and the translation is easy to compute. Formally, it means the translation is polynomial, but it still can have a huge exponent. So there are some translations from some problems where you then end up with n to the power of 6. So the set problem is n to the power of 6 times larger than the original problem was. So it's not fully universal, but it works for a lot of things. And the heuristic, surprisingly, also worked for other problems. For other problems where people try to write their own solvers for solving solving graph colorability, and then someone comes up and just uses a set solver with a naive transformation, and it's faster. So this happens. Yeah. Yes.
Can you also use non-interpreted functions as arguments, and do you support quantifiers, first-order quantifiers in answer set programming?
In answer set programming, we have first-order quantifiers. So the variables x and y here, they are first-order variables.
Okay.
The problem, however, is that we need to apply some specific restrictions. And if you want to have function symbols, because for getting down to a set problem, we have to ground the first-order variables, and the grounding itself can be of exponential space, in general. Yeah. But in practice, it often works very well. Yes?
Are there other MP problems which are currently attacked? Can these results compete with the set solver?
There is the CSP community, which is constraint satisfaction problems, which means I have statements like where I don't assign to a variable, I don't assign the value true or false, but I can assign a number to it, and then I can say, okay, the number of apples in my solution should be less than the number of bananas, whatever. They are also very efficient, yeah. And there is some very good interlinking between those. Originally, answer set programming also was kind of doing their own stuff, and then they realized, okay, we can borrow a lot of the techniques from the set solving guys. So there is a lot of interconnections and ideas flowing in one direction or the other. And sometimes the ones are faster, then they are adopted, and then in the other area of research, some new things pop up. Yeah. So it's not in general that the set solvers are the best. Yeah.
So you're also looking into finding optimal solutions with respect to some cost functions. First, you mentioned set 3, which currently has the Pareto set 3 optimization thing. Do you do similar things in answer sets?
Yeah, there are weight constraints,
okay,
which enable something similar. Yeah.
All right, thank you.
Yes.
So what about making mathematically rigorous theorems, like saying in which case this works better than something else? Do you have something like this?
If I have some theorems about average cases.
Yeah, let's say, some mathematical stuff, not like.
I didn't bring any with me. So there are, for some of the techniques that I showed you, there are mathematical theorems showing why they work. So for example, this learning, I think they really have proofs that specific learning schemas give you an exponential an exponential speed up.
This is always worst case analysis then?
Most of the times it is worst case analysis. Yeah. Okay.